Assalamualaikum warahmatullahi ta'ala wabarakatuh, and a very good day. So for today, I'm going to share with you how to design continuous flange beam equal span. So given here the structure layout plan of the building, okay, so based on this layout plan, so I'm going to design this beam. Okay, this beam has equal span because of each span is 7.5 meter and it has 1, 2, 3, 4, 5, 6, 7, 2, 4, 6, 8 span. Okay, so basically we have to really understand how to determine this beam is considered as flange beam. It is because this beam is connected with the slab. So when this beam is connected to the slab, automatically the beam that we're going to design is a flange beam. Okay, so you have to know this is how we're going to determine either the beam is a flange or rectangular beam. Okay. Here are the data given in order for me to design the beam. So which is the given data here, the diameter bar is 12 mm. You may assume in any size 12, 16, 20, 25 is up to you. The diameter length is 8 mm. Concrete grade C30. So it is also depend on the structural purpose. So beam normally at least 30 Newton per millimeter square. The exposure classes depend on the location. Where is the location of the structure that we're going to construct? And then we determine the environmental condition, okay, based on the table given, okay, so which is based on the table 4.1. So how do we going to determine this exposure condition? I will explain to you again. So normally after we receive the structure or the architecture layout plan, okay, the architecture plan from the architecture firm, there is a detail of the project which is including the location of the project. For example, the project is located at Permatang Pau, Pulau Pinang. Therefore, from that location, we will determine what is the exposure classes related to the environmental condition. So, in accordance to the EN 206-1, Table 3, Table 4.1. So, from that, you may determine the environmental condition and the exposure condition either under XO, XC1, XC2, XC3, and so on. Okay, so here are the other data that is given in order for me to design the structure. Okay, so as usual, the variable variation is based on the usage of the floor. So if the usage of the floor, if a bedroom, okay, or the kitchen, or the staircase, so you have to refer to Eurocode 1, what is the value for the variable action. Okay, this structure is also receive alert from the brick wall 2.6 kilonewton per meter square at 3 meter height with a finisher 0.25 kilonewton per meter square. Okay, the first step is we have to do a preliminary sizing of the beam. So the preliminary sizing, I repeat again, we have to do based on two different calculation. The first one is due to the fire resistance in order for us to know the width of beam minimum. And then the second one is due to the span over depth ratio in order for us to know the H, which is the height of the beam. So in my case here, due to the fire resistance 1.5 hours, for this beam, by referring to table 5.6, the B minimum is equal to 150 millimeter. So therefore, we may provide the width of beam is at least 150 millimeter or bigger than that. And then due to the span over depth ratio, so by referring table 7.4N, so I would like to calculate the height of the beam. Okay, so I choose two span, which is the end span and also the mid span. I would like to compare the value because the ratio for L over D for the end span and also mid span is different. So you have to understand that. So from this calculation, okay, so I get the maximum one is 288. Therefore, the overall depth H usually I'm using this formula 288 plus C nominal plus diameter link plus diameter bar over 2 is 337. I assume that the size of the height of beam is at least 2 times your H. So for 2 times of your B. So sometimes in my case here, so my prediction is I do already have the B here. So if 150, at least I have 300. Therefore, in my case here, okay, I have my H is 337. I assume, you may assume the height of the beam is 400 or 450 is up to you. So in my case, I assume the size is 500. I would like to have more because it is a flange beam. So because the height of the beam is including the height of the slab thickness. Okay, so width of the beam is at least 0.4 H, or you may have 0.5 H. Okay, it's up to you. So in my case, I would like to use 0.4 H or equal to 200 millimeter. Therefore, my beam size is 200 times 500 millimeter. I hope that you have no problem in order for you to do a preliminary sizing of the beam for the structure that you are going to design. So we will continue on the nominal cover. So on the nominal cover, as usual, we have to determine the nominal cover based on this equation. C nominal is equal to C minimum plus C deviation. You may refer to clause 4.4.1.1 in your Eurocode, okay? So the minimum cover, C minimum, you have to check or compare between these three value, which is due to the fire resistance, due to the bond requirement, and due to the exposure class. So we go one by one. Due to the fire resistance, the C minimum is referred to table 5.6. Okay, 5.6 is minimum dimension and exit distance for continuous beam made with reinforced or pre-stressed concrete. So I do have 1.5 hours. Therefore, my C nominal is in between 150 to 250, which is 25, between 25 and 35. So I took 30 as I did an interpolation, so I take in between, therefore it's 30. So means that your alpha is 30 because your alpha SD is alpha plus 10 minus diameter link minus diameter bar over 2. So my alpha based on table 5.6 for continuous beam is 30. So my answer for C minimum due to the fire resistance is 26 mm. Due to the bond requirement, you may refer to table 4.2 minimum cover C minimum B requirement with regard to bond. So it's equal to diameter of bar, which is 12 mm. I'm using the arrangement of bar separated. Then the last one is due to the exposure condition. So the exposure condition, you have to refer to table 4.3N. In my case here, by referring 4.3N recommended structural classification, the strength class is C30, which is the exposure class is XC1. C30 or 37 reduce class by 1. Therefore, by referring table 4.4 and values of minimum cover C minimum durability, I have to reduce class by 1 from S4 to S3, which is equal to 10 millimeter. So therefore, my C nominal is equal to C minimum plus deviation. So C minimum, compare these three value between C minimum due to the fire resistance, due to the bond, and due to the durability. Which one is the bigger one or the maximum one become your C minimum. Therefore, in my case, the C minimum is equal to 26 millimeter. And then plus with the deviation value is used in a country may be found in the national index, then the recommended value is 10 mm. Then I got the answer here, C nominal is equal to 36 millimeter. So I run out into the nearest biggest 5, which is 40 millimeter. Why? I didn't use straight away 36 millimeter as my nominal cover because it is the it's quite difficult for the general worker to measure 36 millimeter in order to place or to locate or to put in the reinforcement for this for the beam, so for the structure. So it's quite easy for us to measure 5 mm, 5 mm, 5 mm. So that's why round up into the nearest biggest 540 millimeters. We do a design action. So in order for us to do the designation, first we have to analyze the slab. Either the slab is a one-way or two-way slab. So in my case here, so the slab length here, Ly and also Lx is same, which is 7.5 meter. So therefore, 7.5 divided by 7.5 is equal to 1. The slab is a two-way slab. Another thing is because this slab is a square slab, that's why the area of the load that is transferred to the beam is triangular load. So same for all of the cases. So here are the free body diagram how the load transfer. So here is the action from the beam, action from the slab, action is also from the slab. We have a two slab here. So means that we have to total up the load here. Okay, so the first process, we have to calculate the load on the slab. In order for us to calculate the load on the slab here, so we have to calculate the permanent action of the slab surface, which is 225 times 0.11, which is equal to 2.75 kilonewton per meter squared, finishes 0.25 kilonewton per meter squared, and the total permanent action GK is equal to 3 kilonewton per meter squared. Therefore, the total N is equal to 7.8 kilonewton per meter squared. Then we have to transfer load from the slab to the beam by using this formula, because this is a two-way slab and it is a triangular shape. That's why we're using NLX over 3. Then the answer here is 19.5 kilonewton per meter. Note that here, all the load transfer values is assumed same in this plan due to same floor function and load acting on top of the slab. So means that, okay, all the slab function here is considered as the same. So if you have a different function of the slab, you are possible to have different variable action of the load that may cause the load here, okay, and this slab will be different. So you have to be careful on that matters. Next, we have to calculate the load on the beam, which is the permanent load, which is the surface of the beam, and then the brick wall, and the total GK is 10.55 kilonewton per meter. Then the design action N is equal to 1.35 GK. So here I'm only calculate the permanent action, okay, due permanent action, okay, not the variable action, because of the variable action is already calculated on top of the slab. So it will transfer from slab to the beam. That's why on the beam itself, the load is only permanent action. So how do I get this 53.24 kilonewton per meter? As I said before, it is total up from this beam, okay, and also this slab. So action on top of this beam, slab, and this slab. So we have a two slab, 19.5 kilonewton per meter here, times 2 plus with 14.24, we will get 53.24. So beam can consider as equal span if the difference between shortest and longest span is not more than 15%. Next process, we have to draw the shear force and also bending moment diagram. In order for you to draw the shear force and also bending moment diagram, it's same as a rectangular continuous beam. So you have to refer to table 3.5, okay, design ultimate bending moment and shear force. So you have to identify which one is the outer support, near middle of end span, at first interior support, at middle of interior span, and also at the interior support. So here is considered as the outer support, both sides. So this is first interior support, this is considered as a first interior support, then the rest is the interior support. Here is the near middle of end span, this is a middle span. Then here is the first interior support. Then this is the interior support. Then the value of the shear force and also bending moment is referred to table 3.5 design ultimate bending moment based on the condition of the support and also mid-span. Then we have to calculate F. F is equal to WL. W is the load that you get, 53.24 kilonewton per meter, time with the length 7.5 meter. So here 0.45 F for the shear force is equal to 0.45 F is equal to W times L. You will get 179.69 kilonewton. You do for the rest. Then bending moment here, okay, is 0.09 FL. So F is actually WL and then time with another L. Okay, so you have to remember the L that you have to use is L of the span, which is length of each span, not for the whole span 7.5 time with each span. It is wrong. So each span is a single span. Okay, so you have to remember that. Next process, you have to determine the effective width of flange because this is a flange beam, as I said before, because the beam is connected to the slab. So in my case here, so here is the section of the beam that I'm going to design. So which is, this is actually the perpendicular section, okay, to the beam that I'm going to design. This is actually, okay, this is actually, okay, this cutting section. Okay, this cutting section. Okay, this cutting section is the section that you're going to calculate your BEFF. So you will have this one BEFF and then the second one the BEFF. So here is consider your BEFF at end span. Here is your BEFF at the middle span. That will differ in terms of your L naught. So here you will use 0.85 L naught. Here you will use 0.7 L naught. Okay, so the span is still 7.5 meter. Okay, so look here. Okay, so the BEFF, okay, for the end span, BW plus BEFF1 plus BEFF2 is less than B. So it is considered of end span. That's why your L naught here, you're using 0.85 L. By referring to figure, I have to check it first. Okay, by referring figure in your appendix. Okay, figure 5.3 effective flange with the parameter and figure 5.2 definition of L naught for calculation of effective flange width. So when your flange here, okay, is located at your end span, that's why I'm using your L naught is equal to 0.85 L. So that's why I'm using this value. So I'll get B1 and equal to B2 is equal to L minus BW over 2. So this is length of the perpendicular section. Okay, so 7,500 minus 200 over 2 is equal to 3650. For example, okay, this perpendicular section, in order for make you not confused, okay, which length that you have to use, okay, this is actually that L is actually, okay, this length. Okay, this length, this section. So for example, if this section is 5 meter and then this section is 7.5 meter, your B1 and B2 will have a different value. So in my case here, my section here, the length of this span and also length of this span is same. That's why I consider my B1 and also B2 value is considered same because the length is same. So if you have a different length, therefore you will have B1 and B2 value different. Okay, so you have to be careful on that, and then you will get your BEFF1 should be bigger than less than 0.2 time with the L naught. So if you get more, you have to use the lesser one, 1275. Then BEFF is equal to BW plus BEFF1 plus BEFF2. You will got 2750, and then it should be less than your B. B is equal to B1 plus BW plus B2. So BEFF is equal to 2750. So at the midspan, okay, so you have to repeat the same method again, or the same step again, except the L naught here is different, because the L naught here is using the midspan, because we are going to calculate for this beam, okay, this beam, okay, this beam, the rest, this beam, okay, which is 1 2 3 4 5 is at the mid span, okay, this one is at the end span, so the value is different, so that's why I'm using that value, okay, 0.7 L naught, okay. So then the same process again you have to do. Then I got the answer BEFF is equal to 2300 millimeter. And then you start to design the main reinforcement. So as usual, you have to calculate the effective depth, H minus C nominal minus diameter length minus diameter bar over 2. I got 446 millimeter. And then you have, because this is, okay, the flange section, you have to check the beam that you are going to design either using the flange method or rectangular method. You have to be careful on this. So here, I check for both condition at end span and also mid span, because the BEFF value here is different. So I check the end span first. So MF is equal to which is the flange moment, okay, equal to 0.567 FCK, BFHF D minus HF over 2. I got 2012 kilonewton meter, and then the M is less than MF, the neutral axis lies in flange, therefore designed as a rectangular section. For the midspan, I got the same answer. You have to remember your BF here, so you have to use BEFF for midspan 2300. Then I got the conclusion here, M is less than MF, the neutral axis lies in flange, designed as your rectangular section. Then the first one, you have to calculate AS minimum and AS maximum. So you have to make sure that the result that you get further is in between AS minimum and AS maximum for the main reinforcement that you're going to design. Okay, here, in order for you to start the design, okay, in my case here, I will design for each span because they have a different condition, in order for us to make sure that we're going to have an optimum design for the reinforcement. So I will start with the near middle of end span. The moment is 269.53. So you have to remember, when it is end span or the middle interior span, okay, not at the support, okay, at the mid span, okay, you have to design as a flange section. So based on the result that you get. So if M less than MF, therefore the neutral axis lies in flange, designed as a rectangular section. So that's why I'm using the method here is a rectangular method, but the difference here, K equal to M over BF D squared FCK. So if it is a normal rectangular beam, okay, it's not a flange beam, you use BW here, okay. So at the flange section, so I'll get the answer 269.53 times 10 power of 6 divided by 2750, which is BEFF for end span, time with 446 squared times 30, I'll get the compression reinforcement is not required because the K value is less than K balance. Then I calculate the Z value and then the AS value here. So 1462 millimeter squared. Then I provide 1610 millimeter squared to H32, and then it's in between minimum and also maximum. Second one, at the middle of interior span here is the difference. Okay, we already know that although it is a flange section, because the condition of M is less than MF, we design as a rectangular, we using a rectangular method to design. Then you have to use a BEFF for the interior span, which is 2300 here. So I'll get the answer, compression reinforcement is not required, therefore the beam is singly reinforced. So I'll get the answer for H201260 millimeter squared in between AS minimum and AS maximum. Here I'm going to share with you about the support. Okay, for the support, no need to check either the M is less than MF or M is more than MF. Okay, So it's straight away condition. So you have to design at the support as a rectangular section. So the B that you have to use here is BW. So M over BW D squared FCK. So I'll get the answer here. It is a doubly reinforced. So you have to check D prime over X is less than 0.38. I got it less than 0.38. Therefore, I have to provide the AS prime, which is the compression reinforcement first. Okay, 763 millimeters squared by using this formula. This formula is inside your reference or your Eurocode. Okay, so provide for H16 804 millimeters squared. So this prime D prime over X is the process that we have to use to determine which formula that we are going to use in order for us to calculate this AS. Okay, so if it is less than 0.38, so we will use this method, then we'll get the answer. So you have to remember here, the AS prime that you have to use is actually AS prime required here 763, not AS prime provided. So I'll get the answer for H25 1960. The answer is in between the minimum and also maximum value. Next process, you have to calculate for the interior support. So the K is also doubly reinforced. Okay, so I'm using this formula. So you may use both formula, either D prime over A or D prime over D. I'll get the same condition, but the ratio is D prime over D is less than 0.171 or more 0.171. Okay, in my case here, D prime over D is equal to 0.121 is less than 0.171. So I show to you the both method that we can use in order for us to determine the calculation of AS area required, area of tension reinforcement required that we would like to determine for the beam, which formula that is suitable or that we can use in order for us to provide the tension reinforcement. So we can use either D prime over D or D prime over X. So both formula can be used to determine which formula that you're going to use to determine AS area of tension reinforcement required. Okay, so I'll get the answer here for compression reinforcement. At the top is 2H16 402, and then for the tension reinforcement 3H25 1470 is in between. Okay, AS minimum and AS maximum. Design the shear force as usual. We have to determine your VED is equal to Vmax. Okay, is from the first interior support, and then you have to calculate of VRDC. Okay, VRDC and also Vmin. You have to compare which one is the bigger value. So in my case here, VED is more than VRDC, so shear reinforcement is not required, therefore provide minimum shear link. So as usual, you have to check this K and also rho 1 value. The K value should be less than 2, rho value should be less than 0.02. Okay, so you use this minimum formula for shear link, then I'll get 0.175. Therefore, the answer here is H8 300 center to center. Next process is a deflection in order for us to check either the beam is passed due to the deflection, the applied load, under serviceability limit state. So I got, by comparing rho naught and also rho naught is less than rho, therefore using this formula, I'll got L over D basic 17.56, and then L over D allowable is 17.56 times with modification factor of the reinforcement, AS provided over AS required, modification factor of the span, because the span is more than 7 meter, that's why we have to calculate the modification factor of the span, which is 7 over L effective. So L effective is 7.5 meter, and then modification factor for the flange, because it is flange beam, we have to calculate, we have to time with 0.8, then we will get L over D allowable here. So L over D actual here is 16.81, and then we'll get here the deflection check fail. What we have to do, if we get the answer L over D actual is more than L over D allowable, therefore the deflection check is failed. So we have to increase the beam depth H, because it's reflect the D here. Okay, so means that they will reduce the L over the actual ratio. And then we may reduce this beam span length by adding the column in between the beam. Therefore, we will have an extra span. We will shorten this short short. We will have a shorter span compared to the span that we have now. So after we change all the things, as usual, we have to redesign the beam after changing the beam configuration and dimension from the beginning. So we have to do the same process again and again. Okay, then a crack check here. So my crack check here, so Fs is equal to Fyk times Gk plus 0.3 Qk. So how do I get this 18.05? 18.05 actually unaffected load of the permanent action from the slab and also beam. And then here is the variable action from the slab. Okay, so that we already transferred to the beam. Okay, so you have to remember how to calculate this. Okay, so here, how do I get this 18.05? So by adding load from the beam, okay, permanent action from the beam, okay, without factorize, okay, plus with the permanent action from the slab that is already transferred to the beam, okay, your NLX over 3 without factorize it, okay, so you will get this 18.05. Okay, so and then as usual, so I have 2H32, so I'll get one spacing here. So the deflection check is passed here by using this formula, B minus 2C nominal minus 2 diameter length minus 2 diameter bar over 1 spacing. So it is the actual spacing of the bar is 40 millimeter, which is bigger than S minimum and lesser than S allowable. So S allowable is as usual from the interpolation from the table table 7.3 and maximum bar spacing for crack control. Okay, here is the detailing of the beam. Okay, so we have to draw the longitudinal section and also cross-sectional of the beam. So here is for the near middle of end span. Here is the middle span. Here is the support. So you have to draw the longitudinal section of the beam for the whole span and also the cross-sectional. So I hope that by this explanation, you know how to design the continuous flange beam equal span. So you also have an idea to differentiate between rectangular beam design and also flange beam design. So if you have any question, you may email to me, you may come and see me, you may comment, and also you may DM me for any inquiries. So that's it. Thank you. Assalamualaikum.